Hello everyone, in this video we're going to go over some sections 5.6 class problems. So first, let's consider some sequences and see how they operate. Here we have recursive sequences. So we have A0 being 2, A1 being 5, and we have the general AN equals 3AN minus 1 minus 2AN minus 2 for n bigger than 2. So now we want to find the terms A2, A3, A4, and 5. So to work A2 using this this rule, we're going to have that is 3 A1, since it's n minus 1, 2 minus 1 is 1, and twice AN minus 2, so it will be 2A0. Now, we do have A1 and A0, so we have 3 times 5 minus 2 times 2. And so now this is 15 minus 4, this is 11. Now A3 is going to be in the same way, 3A2 minus 2A1. And so we're going to have that this is 3 times 11 minus 2 times A1, which is 5. And so now we have 33 here minus 10, so it's going to be 23. Now A4 follows the same rule, 3A3 minus 2A2. And so now this is going to be 3 times 23 minus 2 times A2, which is 11. And so now at this point, this is 69 minus 22. And this is just going to be 47. And last, A5 will be 3A4 minus 2A3, which will be 3 times 47 minus 2 times 23. And so now this is going to be 141 minus 46, which is going to give me 95. Now let's go to question number 2. So for question number 2, we have consider the following sequence. We have B1 being 1 and Bn being 2Bn minus 1 plus 1 for n bigger than 2. So once again, this is a recursive sequence. And if we want to find out B2, then this is going to be 2B1 plus 1. And B1 is 1, so this is 2 by 1 plus 1, which is going to be 3. B3 is going to be twice B2 plus 1. So it's going to be 2 times 3 plus 1. The 6 plus 1 is 7. B4, 2 times B3 plus 1. And so now B3 is 7. So 2 times 7 plus 1. So 15. B5 is 2 times B4 plus 1. So this is 2 times 15 plus 1, which is 31. And B6 will be 2 times B5 plus 1, which is twice 31 plus 1. And this is 62 plus 1, 63. So as you can see, this is all the time about getting the previous value to get the next value. Now on the Fibonacci, when we're trying to find the first 8 terms, we already have the first two, F0 and F1. So we're going to go for F2. And remember, Fibonacci is just the sum of the previous terms. That's how the sequence of Fibonacci came into play. So we have F0 and F1. So we just need to find up to F7. So this is going to be F of 1 plus F of 0, which is 1 plus 1 is 2. F of 3 will be F of 2 plus F of 1, which will be 2 plus 1 is 3. F of 4 will be F of 3 plus F of 2, which will be 3 plus 2, which is 5. F of 5 will be F of 4 plus F of 3, which is 3 plus 5, which is 8. F of 6 is F of 5 plus F of 4, and that's just 5 plus 8, which is going to be 13. And last, F of 7 is F of 6 plus F of 5, and this is just 8 plus 13, which is going to be 21. So everything is about having the sequence. For the Hanoi Tower, that Hanoi Tower was a little bit difficult to realize the sequence, but once that you have the sequence, it's not really that bad because at this point, do you want to know how many moves it takes to transfer phi this? So do you want to find out what is m of 5? But you can just simply start from the point that you need. So m of 2, we have m of 1 is equals 1. So m of 2 is just going to be 2, m of 1 plus 1. And so this is just going to be 2 times 1 plus 1, which is 3. So notice that that's pretty much the same sequence that we have over here. This is exactly the same sequence with the Tower of Hanoi. We just want to get to 5. So if we follow this pattern that we use here, M3 was 7, M4 was 15, and M5 was going to be 31. It's just that now it has the meaning of the Tower of Hanoi and for transferring the disk. We can keep going. Now M of 6 is just going to be 63 that we get from here. And so we want to get to M of 10 in here because we want to transfer 10 disks. So we're going to do 2M of 6 plus 1. So this is twice times 63 plus 1. And so that's 127. M of 8 is 2M7 plus 1. This is just twice 127 plus 1, which is 255. And similarly, I can go with M9, which is going to be twice 255 plus 1, which is going to be 511. And now M of 10, twice 511 plus 1, which at the end is just going to give me 1023. Okay? So it takes 1023 movements to transfer 10 disks. Now, this is about finding a specific numbers, but now let's go the other way around. Let's go with the sequence that we already have the numbers, but we want to find out some sort of sequence that provides me with these numbers. So notice that the difference between the first and the next is 3, and also between the second and the next one is 3. So we can kind of start with saying, hey, A1 is 1 because that's the first term. And then the AN is just going to be the term AN minus 1 plus 3. And we can think of this as something that goes from N equals 2. Notice that it holds the difference. A2 is going to be A1 plus 3. So it's going to be 4. And we continue to get that always. Or if you're starting from 0, you can think of this as A0 this. AN is AN minus 1 plus 3. And then you can start from N equals 1. Now, we want to do something similar, define the same recursive sequence that produce 2, 6, 18, 54, 162. So this one is a little bit more complex, but notice that we do have that A1 is going to be 2. And so we now can see that the next one is the one that we have before, but multiplied by 3. 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. And 54 times 3 is 162. So we can think of A1 being 2. And now AN is just going to be 3AN minus 1 with N bigger or equals than 2. Or also, if you think of this as A0, then you can set it up as the same, but with N bigger or equals than 1. So it all depends of what you're defining at your first term. Now let's go to question number 7. So this is consider A1 equals 2 and AN equals AN minus 1. For N bigger or equal than 2, we want to find a couple terms. So what is A2 according to this? is just going to be a1 squared, which is 4. a3 is just going to be a2 squared. So that's going to be 4 squared, which is 16. And then a4 is going to be a3 squared, which is going to be 16 squared, which is going to be 256. So this is one way of seeing this, but notice that this is like 4 is 2 to the 2, 16 is 2 to the 4, right? And 256 will be 2 to the 8. So if we're going to find a specific formula for an, we'll say that an is twice. So notice the pattern here. A1 is equals 2. A2 is 2 to the 2. A3 is 2 to the 4. And a to the 4 is 2 to the 8. So this is like powers where the exponent is also a power of 2. So notice that this is going to be 2 to the power of 2 to the n minus 1. Because notice how it's growing the exponent. First is 1, then it's 2, then it's 4, then it's 8. So the exponent has a sequence 2. This is 2 to the 0, 2 to the 2, 2 to the 4, 2 to the 2 to the 3, 2 to the 3. So with n being bigger or equals than 1, then notice that we're going to have this starts at 2 to the 0, 2 to 1. When n equals 2, this becomes 2. When n equals 3, this becomes 2 to the 2. So it matches these numbers here. Now for question 8, we have the factorial that can be defined recursively. And so 0 factorial is 1. N factorial is n times n minus 1. We want to use this to compute 5 factorial. So remember, 5 factorial would be 5 times 4 factorial, according to this sequence. But 4 factorial will be what? Will be 4 times 3 factorial. So 5 times 4 times 3 factorial. But what is 3 factorial? 3 factorial is 3 times 2 factorial. So 5 by 4 by 3 by 2. And so in the same way, we can continue. We're going to find out that this is by 5 by 4 by 3 by 2 by 1. So we get to the point where this is just the last point, because 0 factorial is 1 times 0 factorial. And so the multiplication of this will be 20, 60, 120. Okay. Okay, here in question number 9, we have a very similar type of sequence to recursive sequence to the idea of what we have for Fibonacci. Actually, 9 and 10 are very similar. So S of 1 is 1, and S of n is going to be S of n minus 1 plus n. So if we're going to find the next terms, for example, we have S of 1, it's just going to be S of 0 plus 1, which is just going to be 1 plus 1 is 2. Now, S of 2 is just going to be S of 1 plus 2. So we're using the index here. So we're going to have 2 plus 2. This is 4. S of 3. Then we're going to have here S of 2 plus 3, which is 4 plus 3, 7. X of 4. Then we have X of 3 plus 3. And this is just 7 plus 3. It's 10. And S of 5 is just S of 4 plus 3, which is 10 plus, I made a mistake here. This is 7 plus 4 is 11. And so now we have 11 plus 5. 11 plus 5 is 16. So once again, to recap, I made a mistake here. Instead of adding the right number, which is 4 and 5 respectively, to the previous number. Okay, so we get 11 and 16. Now, we want to find a explicit formula for this, but the way that we can do that is we can go recursively back. So S of n is just going to be S of n minus 1 plus n. But at the same time, we can now go and do S of n minus 1 is going to be S of n minus 2 plus n minus 1 plus n. And then I can go, well, S of n minus 2, I can return to S of n minus 3. And so it's going to be S of n minus 3 plus n minus 2 plus n minus 1 plus n. So I can continue going backwards, and I can reach to S0, and then I'm going to have plus 1, plus 2, plus 3, plus, n minus 1 plus n. So really, I'm doing S of 0, which is 1, by the way. Yeah, I use double this here. I don't need this one double time here, since S of 0 is 1. So at the end, this is just going to be the sum from 1 to n of k, for k equals 1 to n. And if you remember from our series, this is just n times n plus 1 over 2. So yeah, so this is just going to be, wait, no, we do have this 1 here and then the s here. So it's, at the very end, s of n is just going to be 1 plus n times n plus 1 over 2. Yeah, because we do return to s of 0 regardless of what we have from before. And we do have this 1 here from the end. Okay, so if it's this, then we're going to have at the very end that s of n is going to be this, which is n squared plus n plus 2 divided by 2, and just simplify. Now for the Lucas numbers are really similar. It's just now the starting point is going to be L0 equals 2 and L1 is 1. And so it's always about the sum. So we have that L2, which is the next year, will be the sum of L1, L2, which will be 3, the sum of this 3. Now L3 will be this was L0 plus L1. And then now there will be L1 plus L2, which will be 3 plus 1, which will be 4, because L1 is 1. Okay, and so now L5 will be L4 plus L3. Sorry, this is L3. This is L4. This is L3 plus L2. And so it's 3 plus 4 is 7. Now L5 is L4 plus L3. So now we have that 7 plus 4 is 11. And we want to L6. L6 is going to be 18, the sum of these two. L7 is going to be 18 plus 11, so it's going to be 29. And L8 is going to be 29 plus 18, which is going to be... well, I only need to get the first 8, so we're reaching L7, we're good. Okay, but well, the next number, the L8, will be 18 plus 29. All right, so let's move to this question. We have a bank that earns 5% per year, and Bn is the balance after n years, starting with 1,000. So let's write a recursive sequence for this. Well, notice that the balance in the end year is just going to be the balance in the year n minus 1 plus the 5% of interest on the year n plus n minus 1. So notice that we can kind of factor the bn plus 1, and this will be 1.05 bn minus 1. Okay. So this will be the initial recursion, and we're having that BC here as 1,000. So that pretty much completes the recursion overall. And this is going to give me for n bigger than 1 this. Now we're going to compute B1, B2, B3. We'll just plug in here. So B1 will be B0 times 1.05, which is 1,000 times 105. B2 then will be B1 times 105. But notice that B1 was this. So we're going to have 1,000 105 square. And now B3 is going to be B2 times 1.5. So that's just going to be this times 1.5. So I'm going to get 1,000 1.05 to the 3. So notice the pattern. B3 gives me this power to the 3. So the explicit formula for n is kind of easy. 1,000 times 105 power to the n. It's just explicitly for the year n. This is going to be composed n times, which is actually how the compound interest is going to work out. All right, so this is the end of the examples for section 5.6.